Welcome back. Let's get stuck into correlations and covariations. So, I guess the point that I've tried to articulate thus far in this intro to this lecture is that the world is made up of covariations. So, as one measure changes, the other measure may change in either a similar or opposite direction. And here are some news headline examples which say droughts mean fewer flowers for bees. An extra glass of wine a day will shorten your life by 30 minutes. And shark attacks increase in El Nino years, says a marine biologist. So all of these are really reflecting relationships between measures, right? So for the glass of wine a day, we see that as wine consumption increases each day, the lifespan decreases, right? And so these are the relationships that we're thinking of. Now, a good critical thinker will look at news headlines like this and ask themselves, well, are these relationships explained perhaps by some other variable that's accounting for the relationship between these two things? Or is it possible that this actually reflects how the world operates? And so that I think is the nuance that's required when interpreting correlational analyses in statistics. But they're all around us. And the reality is, this is how we inform decisions that we make, either consciously or subconsciously. If we perform a behavior over and over and over again, and we see it's related to some other change in another outcome, then we're more likely to engage in that behavior if we see that outcome repeat itself over and over. And there's a whole science behind this, and you could think about it in terms of conditioning, and there's different factors that influence it. But at a foundational level, when we look at relationships between variables, if as you do something, another thing increases that you like, you're probably more likely to engage in that behavior over time. And so correlations can really allow us to direct how we operate in the world around us. And the fundamental nuance behind this question comes down to causation. Now, you may have heard before the rule of thumb that correlation does not imply causation. And this is true, of course, but there certainly are correlated events that are causally related. For example, every time I switch on a light in this room, in this office, the light turns on, right? So those variables are positively correlated to one another. And I could say with a degree of confidence that they're causally related. So it's really about our understanding of the world around us. And sometimes we can use correlational evidence to allow us to interpret in a causal manner, but only once we have a full understanding of the world around us and also other factors that may explain that. Is it likely that every time I flick the light, something else is happening that's actually turning the light on at the same time, each time, every time? Those plausibilities are in existence, but very, very slim, if not non-existent. Yes, contrary to saying it's in existence, I think you could say with some degree of confidence. And I think it's important because otherwise you have people, and you can look historically, for example, as to the relationship of smoking and lung cancer. And you see these very clear correlations where the more that people smoke, the more likely it is that they develop lung cancer. And if you don't think causally about these relationships and consider other factors that may contribute to these relationships, then you may lead yourself, or we've led ourselves as humanity over time, into delaying interventions that could be put in place to actually mitigate that risk for people. And so, of course, there's other factors. There's tobacco industries who had different interests that contributed to that delay. But fundamentally, whilst we look at correlations, and it doesn't mean causation, it doesn't imply causation just from correlation. You can have causative factors, and when you do, those causative factors are likely correlated. And so we'll get into the nuance of this as we progress through multiple linear regression analyses, and how do we get better confidence in saying to ourselves, actually, the relationships we see between these variables is unlikely to be accounted for by these other factors. And that's really where we get into multiple linear regression. So it builds on a lot of what we learn here. But I think it's important to think about, and I think many times when students learn statistics, this idea of causality is really danced around, or maybe not even mentioned. And I think it's important to say that we do need to consider causality, and in statistics we have ways and mechanisms for allowing us to address this. So in understanding that, I guess it's important to recognize that this is another term to learn when it comes to covariation, and statistics, again, is just a language with a number of new terminologies, and the more that you can really understand what the terms are and connect those terms with their meaning, the better you'll be able to understand statistics. So correlations, it underlies many different statistical analysis we use in this unit, and even more. But for example, we'll talk about internal consistency, regression, like multiple linear regression or simple linear regressions, and factor analyses. So the correlation is really underpinning all of this. So the material builds, so the better you can understand today, the better you'll understand the material as we go on in this unit. So in that thread, let me give you an example of what variance is. And you may have a good sense of variance and what it is in prior statistics unit, but I think it's a really core component of much of what we do in our analyses, and really a framework for understanding the purpose of what we're doing, or why we're doing what we're doing in statistics. And so I want to just cover it here in detail so that you can have a good sense of its meaning and its utility. So variance, what is variance? Well, before that, let's take a step back and say, what are we doing in statistics? What is life? No, okay, I'll go that far back. But what are we doing here in statistics when we have data, and we have all this data on measures that we're interested in, and it can be messy, and it can indicate different things, and fundamentally we want to try to get the stories from the data, try to understand the nature of what's driving that data. And so one way in which we can do that is use things like averages. And we could say, what is the average effect that we see here? And that's actually the baseline model that we use in statistics. When we do things like regression models, we evaluate their effectiveness based on their comparison to the average model, which is just plotting the average line through some data points. So let me give you a concrete example here. Here's an example from Andy Field's textbook, Discovering Statistics Using R. You'll see a lot of these examples today, because I love this textbook and love the examples, and it's well worth a read if you're interested. But this example talks about the number of friends 5 statistics lecturers have, right? And so you ask the first statistics lecturer how many friends you have, and he says 1. The second one says 2. Third and fourth one say they have 3 friends. And the fifth one is just an absolute superstar. Everyone loves him, and he has a whopping 4 friends. So this is out of the norm for statistics lecturers. Usually we hover at the average. And so what is the average number of friends that we have? Often it's 2.6. So that's what this data point says. So 2.6. What do you take away from that? Well, intuitively, what does it mean to have 2.6 friends? And so this is where we need to be conscious of what numbers mean in terms of a statistical sense and what they mean in a practical sense. Of course, it doesn't make sense to have 2.6 friends. You would average that to, on average, around 3 friends, because that's more meaningful. But if you're talking about the numbers statistically here across 5, it's 2.6 friends that are here. And so what we would do to arrive at that number is we would plot the average line there. And what you can see here is that there's a difference between each of these lines. I think I've got a nice slide here. Yes. So what we can do when we're looking at this line, this average line, is we could ask ourselves, what's the total error that we see here? And so this is called the sum of the deviances, but don't worry too much about that. Really what it is a measure of the error. So we have our line of best fit here, which we're using the average in this case, and we're plotting it at 2.6. And we ask each of these lecturers, well, how does this reflect how many friends you have? And so for the first lecturer, which is x1, here it's xi because I represents each of the individual lecturers. So the E letter here on the left is the sigma, and then you have xi, which is each of the individual lecturers and their score, and then you have x bar, which is the mean. And so to work out the total error, we see what the difference is between, say, lecturer 1 and the mean. So lecturer 1 has one friend, and mean is 2.6, so the difference is minus 1.6. And then lecturer 2 has two friends, the mean is 2.6, so the difference is minus 0.6. And lecturer 3, you go on to lecturer 3 and 4, who have three friends, the mean is 2.6, so you subtract them using this formula, and you get 0.04, and then finally you get the lecturer 5, the superstar, who has four friends, and the difference is 1.4. And so you can sum the error to see how well your line fits the data, the average line fits the data. And all of this is going to connect to variance very soon, but I really need to start here so that you can build your understanding. But if you have a crack at doing this, if you sum all what this sigma means, if you sum all of these errors, you'll find something interesting, which is that 1.6 minus 1.6 plus minus 1.6 gives you minus 2.2. And then if you add 0.04 to 0.04 to 1.4, you actually get positive 2.2 here. So if you subtract, you actually get 0. And statistically, what that actually means is that all the dots should fit on the line, and you have 0 error. But we don't have 0 error. What's going on here? Well, what's happening is the negative numbers are canceling out the positive numbers. So what do? Well, we actually square all the numbers. Instead of adding them all up as they are, let's just square each of these individual errors. And this is called the sum of squared errors. So to address the negatives and positives canceling each other, we square it. So that's what you see here. So exactly the same formula as before, but we're timesing it by itself to square the errors. And then all of your numbers are now positive. So great. So now you can add up all those numbers using the sum of squared errors, and you get a sense of the total error. And so there's an issue here, though, and hopefully you can identify that, is imagine you have 5 lecturers, and then you collect their data point, and then you have 10 lecturers, and then 15 lecturers, and you collect the data points. The sum of squared errors will always be larger the more data points you have, because you're just constantly adding these squared errors. So we need a way to sort of adjust for this inflation that occurs by the number of people. So we divide by the number of people in the sample. We actually don't. We divide by something called the degrees of freedom, so which is n minus 1. N is the number of people minus 1. But conceptually, you can think of it as the number of people in the sample. But really, it's degrees of freedom. N minus 1 is what we divide by. So here, n minus 1 is 4. So we'll divide all of this by 4. And that actually is what gives us the variance. So what is variance? Variance is the sense of what this error is across this data, right? Variance allows us to understand the overall error that we have. How well our line fits the data is in some ways measured through our understanding of variance. And then there's a special relationship between variance and standard deviation, right? So the standard deviation, if you take the square root of variance, you get the standard deviation. That's why I've actually written s squared in brackets for next to variance, because if you take the square root of that, you get the standard deviation. So if you know the variance, you can actually work out the standard deviation. Vice versa, if you know the standard deviation, you can work out the variance. Standard deviation being sort of the distribution of data around a point. And so that's an important concept to understand when considering what standard deviation means, and the concept of variance, and the concept of total error. Why is this important? Well, I think it frames really well what all of statistics is trying to do. I mean, I think that's a bit of an overstatement, but really what we're trying to do, at least with linear models, is we're trying to get a line to best fit the data, right? And here in our base model, which is using the average, we want a sense of how well does that fit the data. So we look at the error, and for the reasons that we have, is we land on variance to get a sense of how well the data is distributed around that line and through standard deviation as well. So that's what variance is. That's standard deviation's relationship to variance. So really, really useful to know. And this will come back to this point over and over again when we talk about how well the model fits the data. And so it's important to keep in the back of your mind. So coming back to correlations, why do we use correlations and what's the purpose? Well, it allows us to understand the relationship or association or shared variance, right? The shared variance or correlation between two variables. And so to what extent do two variables co-vary, depend on one another, or explain one another? So how could we understand as one variable changes, does the other variable change as well as a function of that? So that's really the purpose of correlation, to understand the relationships between two variables. So when we look at linear correlation, so we are asking the question, to what extent do two variables have a linear relationship? So this is where a simple straight line or a constant relationship. Here's an example of, again, the relationship between amount of money spent on advertising on the x-axis and the number of records sold in the thousands on the y-axis. So we could see that as people spend more money on advertising, there are more record sales that are occurring there. And so to interpret a linear correlation like that, what do we look at? Well, we first look at the direction, right? So we say, is it a positive direction or a negative direction? So here we can see it's a positive direction, because as you go along the x-axis and as it increases along the x-axis, the y-axis also increases. So it's a positive relationship that we see there. And then we look at the strength, how strong is the relationship? So we check the size of the correlation, which can sit between -1 and 1. If it's in the if it's in the positive range up to 1, it's a positive correlation. If it's in the negative range, it's a negative correlation. And then we look at a statistical significance for that correlation. Is there a significant relationship? If we were to look at the null hypothesis, being that there's no relationship between these two variables, how likely is it that we would achieve this correlation under the null hypothesis? And so that's what our p-value comes down to. If it's less than 0.05, then it indicates what we call a statistically significant relationship. Or under the null hypothesis, this would be unlikely to observe a correlation of this size. Here's a formula for the linear correlation. This is using R, and it's what I really want to help you understand from this is there's a lot of information here. The key one is that on the here where you have on the left of the tilde, this is your dependent variable. So your formula for a regression model is going to have the dependent variable or the outcome variable here. So here it's sales, so number of album sales that are there. And then here on the right-hand side is the independent variable. And so it's the number of amount of money spent on advertisement. And the one, don't worry about it for now. It's really just a part of the model that says the intercept is free to vary, so it doesn't have to go through 0. It can sit wherever. Because here you can see that the intercept hits at 120 million or so. And so, well, actually, the intercept sits at 134. So that number here, this estimate shows where it crosses the y-axis. And so this must be 134,000 record sales. And so the interpretation here, the thing we focus on is this beta estimate. Now, e to the -02 just means move the decimal spot to the left 2 spaces. But I think this is in hundreds of thousands, the thousands of dollars. It's in thousands of dollars. So what we'd need to do is actually move it back to the right, I think, by 3 decimal places. So overall, the decimal place goes to the right by 1. So what this means, if we were to interpret this, it means that for every 1 unit increase in or $1 spent on advertisements, you get 96 additional record sales. And so that's the positive relationship that we see there. Some other key things that we see, and then the statistical tests show that it's significant, so it's less than 0.05. Some other key things to take away here is this F statistic, right? Remember I said that the baseline model is just the average of the model, and this F statistic is essentially comparing the model that we've generated here. So this regression model or correlation that we see between these two variables, it's comparing that to the average. If we were to fit how much better is this model than using just the average number of record sales? And you can see that if you have this line here versus like a line down here that goes across an average of whatever these record sales are, this line would fit it much better. And so that is why we see the significant effect here. So it's saying, look, the model that we've created here fits the data better than the average of record sales. And then the other thing to keep in mind is this multiple R squared. This is the coefficient of determination, right? R squared, and it essentially it comes down to how much of the variance in the dependent variable, here it's sales, is shared with advertisements, right? And so here we see that the multiple R squared is 33%. It says 0.33, but you times by 100 and you get the percent. So 33% of the variance is shared between the two. Now there's this really cool relationship between multiple R squared and correlation coefficient, which is that for simple linear regression models, if you do the square root of your multiple R squared, you'll get your correlation coefficient. So here, when we do the square root of R squared, and I've just put it in brackets here in R to round it to 2 decimal places, you get 0.58. So the correlation that we see here is 0.58. And so I was able to do that by looking at the multiple R squared, the coefficient of determination, and do the square root of that to get 0.58, and that's what we get there. So those are really the key things. We'll revisit this again, but in terms of when we look at multiple linear regression analyses and interpreting the output, but really what I want to take is to show you that they're all related concepts. So correlation, linear regression, they have this relationship between the two, and the relationship here for simple linear regression, that's where you have one independent variable and a dependent variable, is that the coefficient of determination, multiple R squared, when you take the square root of that, gives you the correlation. So multiple R squared is the amount of shared variance. R is the correlation between the two. So we've done all of this. Yeah, so we've checked if, is there a significant relationship? Yes, there is between these two variables. That's indicated by these hashtags because it's less than 0.05. And this, it says 2e to the negative 16. It just means it's very, very small. It's 0.000016 numbers after that. So it's very, very small. We've checked the direction, which is indicated by this estimate here, because we said for every $1 increase in advertisement sales, there's a 96 unit increase in records sold. And then we have that reaffirmed with the correlation coefficient, which is telling us the relationship is positive. So those are all that, and tells us the size of that relationship in correlation measures, the strength of that relationship. Excellent. So what are the types of correlation that we could view? Well, if it's no relationship, R is close to 0, your variables are independent of one another. So they don't covary at all. If it's a linear relationship, so your variables are dependent, as one increases, the other increases, which is a positive correlation, which is what we see here. And a negative correlation is as one increases, the other decreases, negative correlation. So an example of negative correlation is as this lecture goes on, the amount of coffee in my little French press here is, I don't know if it's little, but it decreases, right? So as time goes on, the amount of coffee here decreases. And then we have non-linear relationships as well. which we can look at. So here are some good examples that I've generated to just using synthetic data I've created, and just to show you the nature of what a positive linear relationship looks like. And really the key thing is how you should be reading these graphs, or all graphs, as you say, as we go on the x-axis, what happens to the measures on the y-axis. So as the x-axis increases here for linear positive correlation, and the values on the y-axis increase as well. So we have a positive correlation. Here, as you go up the x-axis for linear negative, the variables on the y-axis decrease, or the data points decrease, right? And so that's how you can get a sense of interpreting information here as well, right? So as you spend more money on adverts and thousands of dollars, you get an increase in record sales, yeah. So that should be the framework you use when interpreting graphs. Here, for nonlinear, it's the same approach. You say as you go along the x-axis, you have a decrease in the y-axis, but then you put a caveat. This is a nonlinear decrease with a sharp decrease in the start period from 0 to 25. And then again, here's a nonlinear graph here that's displayed in this image. So those are different types of correlations that you can see. Excellent. Okay, we'll pause the video there, and then we'll go into the relationship between our understanding of levels of measurement and types of correlations that could be used as a function of that. So take a break, grab yourself some coffee or tea or water, whatever you like, and I'll see you guys very soon.